Okay, let's talk about loops. So loops allow us to basically run a chunk of code multiple times, but maybe with slightly different conditions, or maybe not conditions is the right word, but like we can change some of the values a little bit each time we run it. Okay, the for loop is probably the simplest and most common type of loop in R. You give it a vector, and it can be an atomic vector, it can be a list, and the for loop is going to iterate through each of those elements in that vector and evaluate the code block for each element in there. So here I'm going to say for x in 1 through 10, okay, we want a cat. It's basically kind of outputting to the screen x squared. So it's going to start off when x equals 1, and it will do 1 squared. Then it moves on to the next element in this vector, which is going to be a 2, and it puts 2 squared. Then it goes to the next element, 3 squared, 4 squared, 5 squared, all the way until it reaches 10 squared, okay, 100. So cat is going to output cat x squared, followed by a space, no separators there, and so we get this, okay, 1 followed by space 4, space 9, space 16, all the way up to 100. It doesn't have to be an integer vector like 1:10. You can give it a list here. And so here I've got a list of length 3. The first thing is a vector of length 3, then a vector of length 7, and then a true-false vector length of 2. And we're going to say for basically y, for each element in the list, for y and l, what we want it to do is print out the length of y. So it's going to go to the first element in the list, which is going to be this vector of length 3, and it's going to print out the length 3. Then it goes, once it's done there, then it goes to the next element in the list, which is this vector a, b, c, d, e, f, g. It's going to say what's the length, 7, and it prints out 7. Then it goes to the third element in the list, true, false. What's its length, 2, and it prints out 2. So it can iterate through any vector, whether it's a list or an atomic vector. Here's another example. There's library data sets, and one of the things in data sets is state names. And so we can ask, what are the first 5 states in alphabetical order? We have Alabama, Alaska, Arizona, Arkansas, and California. And so if this is our vector, we can say for each state in state.name 1 through 5, so basically for each element here, we're going to cat to the screen the state. So it's going to start off with Alabama, then we're going to follow it with has, and then we're going to say calculate the number of characters in Alabama, which is 7, and then that's going to be followed by letters in its name and a new line. So Alabama has 7 letters in its name, Alaska has 6 letters in its name, Arizona has 7 letters in its name, so on and so forth. Arkansas, California has 10 letters in its name. And that's your for loop. As far as storing results from a loop, okay, the best case scenario, if you know how many elements you're going to do, is to create a place to store your results and then fill them out rather than trying to grow the object as you go along. But of course, you can only do this if you know exactly how many values to expect. So here I'm going to say, hey, I want to create 10 to the 7, so that's what, 10 million things. I'm going to create an empty vector, repeat NA 10 million times, and then I'm going to fill it in for basically, I do sequence along, the res for results is going to be a vector from 1 to 10 million. And what we want to do is we want to calculate x squared and store it into results position x. Okay, because x is going to start off at 1, 2, 3, and we're going to calculate position 1 through 10 million and store those values. And when we do that, it went through 10 million and it took us 0.64 of a second. So it happened very quickly. Okay. A little bit slower, but this is what you might have to do if you don't know how many results you're going to get, is you just start off with kind of, one element. Here I just start off with a 0, And then I'm going to do the same kind of thing for x in 1 through 10 million. Take x and square it and store it into position x. And so every time I run this, okay, the first time I plug in a 1, then the second time, 2 squared, I get 4, plug that in into position 2, and that requires the results to be resized to accommodate 2 values. Then the third time it has to be resized to accommodate 3 values. And so it takes a little bit longer, not drastically much longer, but about 2.8 seconds to operate this. Okay, so it's a little bit slower than this. Okay. The worst, however, the worst offender would be to start off with some kind of empty vector and then kind of tack on your new result and copy that back into the results. Okay. So basically each iteration copies the current results vector, tacks on, combines it with the latest entry x squared, and then stores that back into results. Okay. So it requires us to kind of copy the current thing and store it back in here. And here I'm only doing 1/100th of the work, 1 through 10 to the 5, 1 through 100,000, not 10 million. And yet this took 13.64 seconds, okay, for 1/100th of the work. So if I tried to do it for all 10 million, then I would take this and multiply it by 100, and that would take me 1300 seconds, which is like, I don't know, 20 minutes or something, okay, a really long time. So we don't want to do that. Okay. So if you know how many values you need, then this is the best. If you're not sure, then this is okay, but you should never be doing this. Okay, a while loop is going to basically repeat until a condition in the while statement evaluates to false. Okay, so here I've got, I start off with I is 1. We're going to take 10 results here. And we're going to say while I is less than or equal to 10, what we wanted to do is we're going to take I squared and store it into results position I. Then we're going to increment I to number 2. And then and this will run until the while statement becomes false. So after that, if I becomes 2, then we do 2 squared position 2. Then I becomes 3. Okay, and it keeps going. And the output is 14916 up through 100. And what is the value of I when this finished? Okay, well, at the 10th iteration, when it stored 100, I was 10, and 10 squared is 100, and stored 100 into the 10th position. Then I becomes 11. Okay, I plus 1 stores back in I becomes 11. It goes back to the top of the while loop, and now it evaluates the statement. I less than or equal to 10, that becomes false. This becomes false, so the loop stops running. It doesn't execute this code anymore. So the loop kicks out, it breaks when I becomes 11. So when we ask what is the value of I is the value 11. Repeat is kind of like a while true. It's just going to repeat forever until the break statement is encountered. So this is going to result in something similar. I start off with I is 1. We have a results vector of length 10. And then first we're going to take I, square it, stored into results position I. So that's going to be 1 squared goes into position 1. Then we're going to add 1 to I. And so I becomes 2. And then we're going to ask if I is greater than 10, then break. So right now I is 2. This is false, so we skip over the rest. We reach the end of the loop, we come back and we say repeat. And so now I is 2, we do 2 squared, so 4 gets stored into the second position. I becomes 3, this is false. We reach the end, now become I is 3, we store 3 squared, and so on until we get to 10. At 10 squared, we store 100 into the 10th position. Then we add 1, I becomes 11. And now we say if I is greater than 10, I is now 11, is 11 greater than 10? That is true, so we hit break. And once we hit break, the loop stops. Okay, if you don't include a break, then repeat will run forever. okay? And if this while statement never becomes false, it will run forever. So sometimes you get stuck in these infinite loops because the thing that needs to happen for it to quit just never happens. So break is going to end the current loop, so kind of your innermost loop that's running right now. Break is going to end that. Next, we'll end the current iteration, but doesn't break out of the loop. It goes to the next iteration of the loop. So here, I'm going to do for I in 1 through 10. So this is the vector 1 through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to say if I is divisible by 2, so if I mod 2 equals 0, so if I is divisible by 2 or if I is even, then break. Otherwise, keep going. And when it keeps going, it's going to cat I to the screen. So what's going to happen? Well, I starts off at 1. This is false. 1 is not divisible by 2. So it's going to output 1 to the screen. Then it goes to the next thing. I becomes 2 in the for loop. Is 2 divisible by 2? Yes. So it hits break and then it quits. So this is only going to output 1 to the screen. Let's look at the next thing. It's the exact same code here, except instead of break, I use next. Okay, exact same code, but now we have next. So it starts off with I is 1. Is 1 divisible by 2? No. So it skips that code chunk. It outputs 1 to the screen. It does cat 1. Then it goes and it says 2. I is now 2. Is I 2 divisible by 2? Yes. So it executes this thing. It does next. So when it hits next, it quits the current iteration and goes immediately to the next iteration of the loop. So it jumps to I is 3. Is 3 divisible by 2? No. So it skips over that code block. It cats 3 to the screen. Then it reaches the end of the code block, so it goes to the next thing. 4. Is 4 divisible by 2? Yes. As it hits next, then it jumps to 5. And so what we're going to end up getting is just the odd numbers printed out to the screen. Because every time I is an even number, it encounters next, and it doesn't run the rest of the code block. It jumps immediately to the next iteration of the loop. We have a couple things like sequence length and sequence along. And these are helpful for creating the indexes for basically the objects that we want, okay? So here, if I have this list, L, that's length 3, I could iterate over the elements of the list, or one thing I can do is I can say sequence along L, and that's going to produce a vector, 1, 2, and 3, to correspond to the elements in L. And then I can kind of subset L based on that. So it's going to say, give me the first element of X. And I can say length of L is that, and store that into position 1. Because sometimes you need to know what position you're in or which iteration you're in. And so having something using sequence along is helpful. And it's going to go through the first thing. It's going to say length 3. Then the next thing, length 7. Next thing, length 2. Okay, so that's sequence along and sequence length. You might say, like, why do I need to do that? Can't I just do like length of L? Length of L is 3, and I can just do 1:3, and that's going to give me 1, 2, 3. Sequence along L will also produce 1, 2, 3, or you can do sequence length of L. Basically, give me a sequence of a certain length, sequence length of 3, and that will also produce 1, 2, 3. And so these all seem like they're doing the same thing. Why do we need all of these things? Well, the biggest difference happens when you have a length 0 vector. Okay, so here L is going to be a list of length 0. And if I do 1: length of L, then it's going to be the same as doing 1: 0. And that vector is going to be 1, 0. And then if I were to try to run this chunk of code, look what happens. Okay, because I'm asking for L double square bracket 1 here, okay, which doesn't exist for this list, then I get a subscript out of bounds. Okay. Meanwhile, if I have sequence length, okay, I have start of empty list, and I do sequence length or sequence along. Okay, sequence along, it produces a 0 length integer vector. And then so trying to run a for loop on a zero length vector for x in basically sequence along L, a zero length vector, nothing's going to get executed. Okay. If you do sequence length of L, so sequence length of 0, you're going to get a zero length vector also. Nothing's going to get executed, no errors there. All right. So nothing executes, but it doesn't produce any errors. Whereas over here, it tries to do something and you just get an error. So using 1 colon length of L can run into issues if you end up with a length 0 vector. When you deal with loops and stuff in R, you might want to try to vectorize your code rather than dealing with a loop. Okay, so loops are fine, but they are slow in R. So rather than using a loop, if you can vectorize your code, it's going to be better to vectorize your code. So a lot of times the performance of your R code can be improved if you're able to think of a way to vectorize it. Now, it's not always possible to vectorize the code. It's not always going to be worth the effort. Okay, and in some cases, it's going to be better to write inefficient code that takes a little bit longer to run than getting stuck for hours trying to think of something that's going to save you a few seconds. Okay, there's kind of this quote from Donald Knuth about premature optimization. Premature optimization is the root of all evil about 97% of the time. But he writes, yet we should not pass up our opportunities in that critical 3% if you are able to vectorize or make your code more efficient. Okay, so here's an example. Okay, so here is a piecewise function. This piecewise function is negative x cubed when x is negative, x squared when x is between 0 and 1, and the square root of x when x is greater than 1. Okay. So here I have a function that uses if. It's going to work, but it's not vectorized. Okay, it says if x is less than or equal to 0, the value is going to be a negative x cubed. Okay, if x is less than 1, I don't necessarily need to check if x is greater than 0 because this is only going to get evaluated when that is false. And so then the value is going to be x squared. And then finally, if that's not true, then we'll use square root of x, and this function is going to return whatever value we get. Okay. If you try to use this function as is, and you apply it to a vector, so here I'm going to create a sequence going from -2 to +2 by 0.01, and I try to throw it into the function f, it's not going to work because x is this long vector, and it tries to do, if x is less than or equal to 0, we get a condition, basically a logical vector of length, whatever, 401 or something. It says condition has length greater than 1, so that's not going to work, okay? And so if I try to plot this, this is not going to exist. What I have to do is I have to run a for loop, okay? And so I'm going to say the values I'm going to plot, we'll start off with kind of 0, along the length of x, and then we're going to say for I sequence along x, and then I'm going to subset x to that ith value. I'm going to run f on x sub I, and then I'm going to store that into plot values square bracket I, and then that evaluates, and now I can plot it, and so here I get negative x cubed, then x squared, and then the square root of x from here. So this is the evaluation of the function there. Okay, another thing we can do is we can run an if-else statement, okay? If-else, here I'm going to break it down, okay? First, we're going to check if x is less than 0. If x is less than or equal to 0, then what we want is negative x cubed. If it's not, then check another condition. I'm going to run another nest an if-else inside there, okay? And so the next thing we're going to check is if x is less than or equal to 1. If that's true, then do x squared. And if that's not true, do the square root of x, okay? So basically it's the same kind of thing that we have going on here, but I'm running an if-else statement, okay? And you can get this real compact inside a function like this. but this might be a little bit tough to read. But I've got if else x less than or equal to 0, do negative x cubed. If else x less than or equal to 1, do x squared, otherwise do square root of x. Then I have my sequence, my vector x from -2 to 2. We're going to do by equal 0.01. Then I can run the function on x directly. Okay, I don't need a loop. I can just take this function f2 and run it directly on x, store it into plot values, and it runs and it evaluates. Okay, and you get that. Okay, sometimes the warning is not, for whatever reason, the warning isn't visible here, but sometimes you get a warning. Okay, and the way if else works is basically it evaluates this statement for the entire vector of x. It also evaluates this for the entire vector of x, and it evaluates this for the entire vector of x. Okay, this square root of x only exists when x is positive. The entire vector of x goes from -2 to +2, and so for everything less than 0, when you ask for the square root of, say, -2, you get an NA, okay? Because the default behavior with type double is it gives us just kind of equivalent to real numbers, and doesn't know how to deal with complex values. So it's just going to give you an NA if you ask for the square root of a negative number. And so it evaluates for the whole thing, and when you get these NAs, you're going to get basically you get warnings there. Okay, so the if else statement evaluates the entire basically true expression and the entire false expression for the entire vector, and then once it has those, then it's going to select values from the true vector where the condition it evaluates to true, and then it selects values from the false vector where that condition evaluates to false. So that's how the if-else statement. Okay. There's also, to improve efficiency, there's also a couple vectorized operations. We have row sums and column sums in R, and they work very fast as far as calculating row sums and column sums for matrices. And if you have a way to kind of make use of these things, you can really speed up your calculations. So I'm going to create like this big large matrix, 1 million rows, 100 columns. I want to find the mean of each row. Okay, here if I say let's subset to the row and find the mean, it takes us a few seconds, 3.67 seconds to do this. We're going to say, you know, for the number of rows we want to do this. But here another option is to use apply. You can say apply the mean function along the margin, and that takes 6.48 seconds. But if you use row sums, okay, basically sum the rows and divide by the number of columns of x, because we just basically want the mean of each row. Look how fast that is, 0.27 seconds. So much faster if you use row sums versus apply or, you know, subsetting to a row and calculating the mean. Okay. Are all of the values that they calculate equal? Yes, they're all equal. So if you do all equal, subsetting the row, finding the mean, applying the mean function across the rows, or using row sums, they all evaluate to the same. So obviously, if you can make use of row sums, that's going to be the fastest. But you know, sometimes you got to puzzle and think about it to come up with a solution. All right, that's that.